Hi all, I'm Alireza Salemi. I'm a second-year PhD student at UMass Amherst. I'm working at SIGIR, and this work is in collaboration with my supervisor, Zamani. So, in this paper, the title is Towards a Search Engine for Machines, Unified Ranking for Multiple Retrieval-Augmented Large Language Models. So I think from the start of this session so far, we learned a lot about retrieval augmented generation, so I won't explain what is retrieval augmented generation. I'm sure that we all know. But as other works also mentioned, that there are generally two ways in the literature that people do rank. The first approach is just selecting an off-the-shelf retrieval model, something like M3.1, Contriver, even Google search to basically retrieve some documents and append to the prompt of the large language model, and then feed it to the large language model to do the generation. It is possible to fine-tune a retrieval model for task-specific using knowledge distillation, end-to-end optimization, or even reinforcement learning. But the thing is that in all of these works, usually we train a single retrieval model for only one retrieval augmented generation language model. However, as an IR community, we had a lot of research about how to basically design search engines. And the thing that we learned so far is that an effective search engine is achieved through aggregating large-scale implicit feedback collected across all the users that we have. And now, if you think about a retrieval augmented generation pipeline, which component is basically the main user of the retrieval system here? The answer is obvious. LLMs. While large language models generate text for the user, but retrieval model has to provide some good documents for LLM to be able to basically generate good text for large language models. So they are basically the main users of large language models. In this paper, we introduce a new problem and also a new ecosystem and framework on how to study this problem. A unified search engine for multiple rank model, and we call our framework and ecosystem URANK. So in the URANK system, we have three main components. The first one is a shared search engine that serves all the large language models that present in our ecosystem. The second component is a set of large language models that each has a utility function that we can basically evaluate to evaluate their performance and basically to evaluate how these retrieve results are useful based on the text that they generate. And also, we assume that each of them perform a specific task that it is known to them. And also, we assume that there should be a bidirectional communication link that the search engine and large language models can speak together using this communication link. And this is an overview of our framework. You can see that the predictive model is responsible for generating the query. Query goes to the search engine does retrieval. It presents the results to the predictive model. Whenever we are talking about predictive model, we mean usually LLMs. And then LLM should consume these results and provide some feedbacks for the search engine, and search engine can filter out for these feedbacks, process these feedbacks, and save them and store them somewhere to later optimize itself. We also introduced a new guideline on how to basically train these search engines for these models. So some of these predictive models may participate in the training and some might not participate. But we assume that any large language model that participates in training, they provide a query set. And for each query in this query set, the search engine provides the search results for each of these predictive models, and predictive models use these results to perform their task. And based on their utility function, they provide some feedback for the search engine, and search engine can store them to later use these feedbacks for optimization of itself. And the main goal of search engine here is to basically change its parameters in a way that result in when it provides some documents for the a user in its basically ecosystem, it gets a higher basically feedback or utility function here. And there are many different ways to combine basically this objective for different users, but it is, I think, reasonable to improve the average performance across all users. So this was basically the guideline, but how we implemented this for this paper to study this problem. For the task, we used a diverse set of tasks here. Some of the tasks are only used during inference. Some of them was both in inference and training. For example, we are working with short-form open domain question answering with datasets like natural question, trivia QA, hotpot QA, which is a multi-hop question answering dataset. And for inference, we only use, for example, SQuad, open version of the SQuad dataset. We also have long-form question answering using Li5 dataset. We have fact-checking with Fever, entity linking using IDA dataset, and slot filling with ZSRE and T-Rex datasets. And all of these datasets are collected from the KILT benchmark. For the implementation of the predictive model, there are two ways to basically implement these models. One of them that we called Retrieval-Augmented LLM is retrieving some documents, concatenating them with the prompt of the language model, and then feed it to the language model. The other way that we can consume this is using Fusion Encoder. In Fusion Encoder, if we have a retrieval list, we concatenate each document in the retrieval list with the question, and then feed this to the encoder of the model. We store the representations for all the documents, then concatenate those representations together and feed it to the decoder of the model to get a single answer based on all the information that we have in all those documents. Aside from that, predictive model should provide feedback, and here we assume that the feedback that large language model provides is based on its performance, only utilizing each document in the retrieval list. And here you can see that the retrieval, the basically language models and tasks that we used. Some of the language models or predictive models only participate in inference, and some participate in both inference and training. And you can see that we have a very diverse set of even large language models. We are using T5, BART, Fusion Encoder. We are using Pegasus. It's a language model from Google. We use Mistral and also Llama 2. And also each of these, it's not in this table, but each of them use, for example, different number of retrieved documents. Some of them use few shot learning, and basically we try to have a very diverse set of users to simulate some real world scenario. And for the search engine, we use a two-stage retrieval process. We use BM25 as the first stage retriever, and then we use cross-encoder as a cross-encoder re-ranking model. We wanted to personalize this cross-encoder re-ranking model for each language model. So for each model, we define an ID, and also we define a task ID, basically the task that this language model is doing. Then we concatenate it with the query and the document and feed it to the re-ranking model to do its job. For feedback processing, we assume that each positive that we get, if it is smaller than a specific threshold, it is a negative document, otherwise it's a positive document. And this threshold can be defined for each user separately. But in this paper, for simplicity, we consider the 0.5 as this threshold. And the way that we train our search engine is by basically using cross-entropy loss. We want to increase the probability of assigning a higher score to positive documents and decreasing the probability of assigning higher score to negative documents. And these are our results, but I know there are a lot of numbers, but let's define some research questions and answer those research questions. So the first two questions that we should ask, how does unified re-ranking perform compared to training an individual ranker for each RAG system? The thing that people have been done during the, basically, in the literature. And the other question is that the same, but we train a retrieval model for all the users that perform on the same dataset. And you can see here the results, but let's go for the findings. When we compare this approach, we can see that URAG outperforms Contriver on for all the users significantly, and for 15 out of 18 of the users for BM25. But on average performance for all users, we got significant improvement in comparison with both Contriver and BM25. The same with the re-ranker individual, and you can see that we outperformed that model for 14 out of 18 users. 11 of them are significant, but on average, again, we get significant improvement against that model. You can see that when we train, for example, a re-ranker on a dataset, because we are increasing the number of users, you can see that the results, it gets better, but still, We outperformed 13 out of 18 users in this case, and they are only the users that participated in training. And 7 of them are statistically significant, but still, on average, we are statistically significant. We have better performance than the other baselines. So this suggests that training a single model based on the feedbacks that we have from all users, all the language models, improves our, basically, the results that we get. The other question is that how does personalizing this retrieval model affect our results? You can here see the results, but again, let's go and see the important findings. We found that personalizing the retrieval model improved the results on average, but the difference is not that significant. But we observed something. So different tasks have different input formats, but the tasks that are similar to each other, like question answering tasks, they have the model doesn't have any way to distinguish these kind of tasks together. And when we do personalization, we see that the most improvement happens for those tasks that have similar input to each other. So we believe that, yes, personalization really does matter, and it's a very important future work that we should move toward that direction. The other question is, how does unified ranking perform on a new RAG system, basically a new language model that uses the observed data sets that we have, the tasks that we are familiar with them? Here, if you look at this, you can see that URAG outperforms BM25 significantly on all the new LLMs on the tasks that it was familiar with them. But when it comes to the, in comparison with their re-ranker dataset, the one that was trained for all the users on the same dataset, they perform very similar to each other. Someone this outperforms someone the other one. And this suggests that data is very important. We will see this sentence a lot in the rest of presentation because data really does matter. The other important questions are, okay, so it's, when we're training a retrieval model for a known RAG system, what if the data set, the task is new, but it is similar to one of the tasks that we did here? For example, the squad, if the domain version of the squad that we didn't have in the training is very similar to NQ. So how does model perform there? Or when the RAG system is unknown but the task is still similar. Or when the RAG system is unknown, the task is but the task is similar to what we had. Or in the most extreme case, what happened when we have a new RAG system on a new data set? Our observation suggests that when we perform on a new task in the training set that is similar to one of the tasks that we have there, URAG significantly outperforms all the baselines. But in the case that the new task is not similar to the ones that we had in the training set, sometimes URAG cannot perform better, and sometimes perform better, but sometimes doesn't perform better. The data is very important. So if we train these retrieval models on a scale on many users here, many language models, it increases the chance of seeing different kind of tasks, different prompts and inputs from the user. So basically covering more of these tasks in our training. The other thing that we studied here is that how does URAG perform when we train it with different amount of data? So we trained our approach with 25%, 50%, 75%, and the full data set for each of the users. And we have quite interesting findings. We found that when we use even 50% of the training data of each user, we outperform all other the baselines. And this is basically proof that, or suggests that this kind of large scale feedback from all users can improve our basically the performance of these retrieval models. In this paper, we discussed the importance of URAG, basically training a retrieval model for multiple retrieval augmented generation, and we show that this approach works very well. This is the first work in this line, but there are many questions that we need to answer in the future work. For example, how we can define better feedback, how to calibrate the feedbacks, what should we do when we have different objective functions per user, or even a user have multiple objectives itself, how we can improve the generalizability of these models, and how we can do online optimization for these models, because it's very expensive. I would be very happy if you join us on my poster session for my short paper. It is very relevant to this, and it is nominated for the best short paper award. And if you scan this, you can find that paper. And thank you so much for your attention.